Hello everybody, welcome back. This is Jonathan Gardner covering Sergey Lang's Basic Mathematics. We are in section 9.2. The title of this section, excuse me, addition, subtraction, and the parallelogram law. So in the last section we talked about what happens if you multiply a point by a number. Well, does it make sense to multiply points? Not really, but what if we added points together, right? It doesn't make sense to add a real number and a point. It does make sense to add points together though. We'll talk about that in a second. So let's say A is the point A1, A2, and B is the point B1, B2, and both of them, A and B, are in R2, of course. Okay, so we're going to define the sum A plus B is going to be A1 plus B1 and A2 plus B2. So we just add the coordinates together. Okay, we add the x coordinates together to get the new x coordinate. We add the y coordinate together to get the new y coordinate. Pretty simple. All right. So let's do some examples. Let A equals 1 comma 4 and B equals minus 1 comma 5. So A plus B is equal to 1 minus 1, that's 0. 4 plus 5 is 9. Okay. Or if we said A is equal to minus 3 comma 6, B is equal to minus 2 comma 7. So minus 2 minus 7. Then A plus B is equal to minus 3 plus minus 2 is minus 5. And then 6 minus 7 is minus 1. All right. Pretty straightforward. We're not going to talk about the graphical interpretation yet. That's the third part of the title of this section. We will talk about some of the properties. Okay. Namely, we have commutativity. A plus B is equal to B plus A, and it should be rather trivial to prove that for yourself. We have associativity. So if we have A plus, and then we do B plus C first, that's the same as doing A plus B first, and then adding C later. Okay. We also have a magical zero element. Okay. So 0, or O, is 0 comma 0. A plus O is the same as 0 plus A is equal to A. So adding 0 doesn't do anything. We also have inverses. Additive inverse. That says that A minus A is equal to 0. Okay? Or we can write A plus minus A if you want. All right, these are easy to prove from the definition here. I'm not going to go through that. It's very trivial. If you're curious or if you want to read the book, you can. Let's just move on with some more fun stuff. All right, if A equals 2 comma minus 5 and B equals 3 comma minus 4. So we have A equals 2 comma minus 5. And B is equal to 3 comma minus 4. Then A minus B, that's going to be A1 minus B1, so 2 minus 3, that's minus 1. And then A2 minus B2, so that's minus 5 plus 4, so that's minus 1. Okay, that's going to be what happens when you subtract those 2 points together. Let's now talk about what this all looks like on a piece of graph paper. I'm going to use a straight edge because I'm not very good at straight lines. So you can see here each inch, these things are lined up at every ½ inch, so we'll count an inch as a point. Okay, and in this case we want to go to positive 4. It doesn't quite line up exactly, it's close though. And we're going to do something like that here for the vertical axis. Okay. All right, so we have the point A equals 1/2. Not 1/2, 1 comma 2. I don't like this marker. So we draw A, 1, 2 is A right there. Okay. Then we have the point B, let's do it in green. B is equal to 3 comma 1. Okay. So B is 1, 2, 3 over here, and up 1, that's B. Okay. Then let's use blue for A plus B. That's going to be 4, 3. So 4, 1, 2, 3. This is A plus B up there. Okay. Well, let's draw some lines now. Let's use yellow here. We're just going to connect the dots here with the origin and see what we get. Okay. All right. We're going to talk about what these lines mean. Do you see this shape? Oh, okay. When we're adding by B, you take whatever point you're at and you add 3 to the right and 1 up. Okay? So this line right here, this is what happens when you add by B. Okay? When you're adding by A, right, if you start at B and add A, then that means go over 1 and up 2. So this is adding by A. Okay? So in a way, you can think of A as equal to 0 plus A is equal to A. So this is adding A here. And then B, origin plus B, is equal to B. So this is adding by B here. Okay? So if you start at the origin and you add A and then add B, or if you start at the origin, add B, and then add A, you're going to end up at the same point. And that's why you get a parallelogram when you add these 2 points together. Now, if you study math in a more traditional way, I want to say traditional, this book is from the 70s. And I think at the time, vectors were avoided until necessary. But this is really what vectors are. Vectors, if you really want to understand what a vector isn't a point. A vector is what happens when you add a point, right? So this vector, like, because the B here, let me explain what I mean by that. So this is the plus A vector here, and this is the plus A vector here. This is the plus B vector here, and the plus B vector there. That's what vectors are. They're basically adding points, okay? They're not points themselves because they're not tied to a point in space, but they are adding points. Okay, that's my little physics digression, okay? So we can see why addition itself is commutative, why that works that way. Okay, all right. What happens if we subtract? Let's get a new piece of paper. Nope, I just need one. So what happens when we subtract? So let's say A is equal to 1, 2, and B is equal to 3, 1. Okay? So what is A minus B? A minus B is equal to minus 2, 1. Okay? So if we were to draw this out graphically, so A is 1, 2. That's A. B is 3, 1. 1, 2, 3, 1. That's B. Okay? And then A minus B, where does that live? So that's going to be over here. Minus 2, 1. A minus B. Okay? Now, this looks a little different, doesn't it? Okay? Let me draw out what I mean. I'm going to draw it this way. First, we have this line here. It goes from the origin to B. Notice that this line is the same direction and same length. Except instead of going this way like you did in the previous example, you're going backwards. So this is minus B. This is plus B. Right? Do you see how that subtraction moves it over here? Another way to think of it is, let's draw where minus B is on the graph. So minus B would be minus 3. 1, 2, 3, minus 1. Okay? So we have a new parallelogram. There's actually 2 of them here. They're both hiding. I'll show them both to you in a second. Okay. Okay. So we have this parallelogram here. I'm not going to draw that point, actually. So this is minus b plus a. This is plus a there. Okay. And then we have a parallelogram that looks kind of like this and like this. I'm ruining my yellow marker by drawing on black with it. That's okay, though. So this parallelogram right here is a plus minus b. Let me draw a different color here. This parallelogram right here, this is a plus minus b. Okay, so this is the parallelogram you get if you add it. Okay, this parallelogram here, this blue one that I'm going to use blue for, this is a minus b. Okay, so you see this parallelogram is kind of flipped from itself across the origin. Anyway, so you can think of it as adding a minus, or you can think of it as going backwards, right? Because the minus b is the opposite vector. That's kind of the lesson there. All right. All right, let A be a fixed point in R2 whose corners are 0. Oh yes, this is cool. Let A be a fixed element of R2. We define the translation of A, so translation, the translation of A is defined to be the association to each point P of the plane to P plus A. So this basically takes the translation of A, takes point P, and it moves it to P plus A. So adding A is basically a translation. And this is where this concept of vector comes from. So we can write this out as P goes to P plus A. This is the translation. Okay? All right. And so we can define that. This is pretty simple to do. I don't think there's much to cover here. So we have the mappings. We have translation, we have scaling, and we have reflection. We haven't done rotation yet. Okay, so rotation is an interesting one. We've done subtraction as well. Okay, so now isometries. Let's go back to section 5 again. Let's review what isometry. So an isometry, this means same. Iso, it means same. And metry means measure. Isometry is a mapping which preserves distance. Okay? Same distance. Distance doesn't change with isometries. Okay? So if we have an isometry F, then the distance from point P to point Q is the same as the distance of point P mapped through F and point Q mapped through F. All right. Which ones of these are isometries, which ones aren't? Anything but scaling so far is an isometry. Okay. The distance between 2 points PQ is dPQ, and we'll use a special symbol for the distance between a point and the origin. Okay, so the distance between a point A and the origin is going to get a special symbol, the absolute value of A. Remember, A is not a real number, it's a point. Okay, so if A equals 1, A1, comma A2, then the absolute value of A is equal to the square root of A1 squared plus A2 squared, because we're subtracting the distance, the point O, which is 0, 0. Okay, we also call this the norm of A. Okay, and if you're into machine learning, norms are pretty important. Now, can you prove that the norm of A is the same as the norm of minus A, negative A? All right, this should be pretty easy because the norm of A is defined to be the square root of A1 squared minus plus A2 squared, and this is the square root of minus A1 squared plus minus A2 squared. So that's pretty easy because you square negative, it becomes positive. That's pretty easy to prove. Now we can also define distance using a new formula, new notation, right? We can say the distance between point A and point B is equal to the norm of A minus B, right? Because now we've defined the point A minus B to be, let's pull out the graph so we can remind ourselves graphically. Okay, so this is A, this is B, this is A minus B. Okay, so the length of this line from here to here is the same as the distance between the points A and B. You see this blue line here and the point blue line there? They're the same. So the distance between A minus B and origin is the same as the distance between A and B. Okay, and we can prove that rather easily. Okay, let's do that very quickly on the margins here. So the distance between A and B is equal to the square root of A1 minus B1 squared plus A2 minus B2 squared, right? Well, what's A1 minus AB? That's just A minus B, A1 minus, what's A minus B? What's the point A minus B? That's A1 minus B1 and A2 minus B2. So this is the same as the distance between A1 minus B and 0. Okay, pretty easy to prove that. We also have the relationship that A minus B, the norm of A minus B is the same as the norm of B minus A, because we can take the inverse of them and it works. Now, we can say that a mapping of f of the plane onto itself is an isometry if and only if for every points P, Q, we have the norm of f of P minus the norm minus f of Q is equal to the norm of P minus Q. F is an isometry. Okay, so these two statements are the same. All right. So now we can rewrite what's the norm of CA. Okay. We can write that as the absolute value of C times the norm of A. Okay, because we can rewrite this way. How can we write that? Well, the distance from the origin to the point CA is the same as C, the absolute value of C, times the distance to the origin of A. All right? So if R is greater than 0, then we have the norm of RA is equal to R times the norm of A. Okay, because R is positive. If you haven't gone through chapter 6, this is a good time to go through chapter 6 and talk about the mappings and how they behave, about images. An image is a set of points that have been mapped. Let's talk about circles. Okay. This is theorem 3. The circle of radius r and center A is the translation by A of the circle of radius r and center O. So the circle with radius r and center C, center A is the same as the circle of radius r, center of the origin O, translated by A. Okay, how are we going to prove this? Okay, so we're going to call this circle, let's give these circles name. Let's call this circle O, and this is the circle A. Okay, so circle O, for each point in the circle X is inside circle O, we're going to say the distance, the norm of X is equal to the radius, right? Because the distance from the origin to the point X is always the radius, because this circle is centered on the origin. Okay? Now, if we were to translate X by A, so we're going to translate X by A. So that takes the point X and it turns it into the point X plus A, right? Okay. Now, this satisfies the condition X plus A minus A has to equal the radius r. Okay. We see that the point X plus A the distance from the point x plus a to a is also equal to r. That's what that means, right? We look at this as a single point, and we see this point minus that point. That means the distance between this point and that is always equal to r. Okay, so let's say y is equal to x plus a, and then we'll find that y lies on the circle centered on the point A. Okay, y is on the circle centered on point A. All right, and this is fairly simple now that we have this analytical method to analyze stuff. You know, it's pretty easy. Okay, all right, let's fill in some more remarks on multiplying by numbers and what that does. So we have associativity. So that means that if B and C are real, then B times CA is equal to B times C, and then multiplying it by A. So we can multiply the point A by C and then by B, or we can multiply B and C together and do A. That should be relatively easy to show. And we can do some distribution. This says that if B and C are numbers and A or B are points, so B and C are reals and A and B are points, then we have B plus C times A is equal to BA plus CA. And we have C times the point A plus B is the same as CA plus CB. All right. And these are relatively straightforward to prove. We also have 1A is always equal to A. That's the identity for multiplication. And we have 0A is equal to the origin. Okay. We will not do the proofs here. They're very easy to prove for yourself if you have some free time and if you're interested and if you like math. These are things you can prove for yourself if you want to. Exercises, there's a lot of exercises for this section. The first part, you're just plotting some points and you are drawing A plus B and the parallelograms that go with it. That's problems 1 through 9. Okay, and then they ask you to do it again, and this time plot A minus B and A minus B. So just draw the parallelograms. 11 talks about a translation. You can prove that it's an isometry, that it preserves distance. We can talk about disks in number 12. Number 13 is going to do some more stuff with circles. This time we're going to reflect the circles through O. We want to see if that's also a circle, and we're going to reflect the disk and through O and see if that's also a disk. Okay. Number 14, you just need to read it closely. This one you're taking and you're basically practicing the distribution of, P minus Q. Draw a picture showing P, Q, A, and Q minus A to convince yourself that this definition corresponds to geometric distribution. Good. 15, draw a reflection through point Q that can be expressed in terms of reflection through O followed by translation. That one's pretty easy. So if you can reflect through the origin and then you can translate it, that's the same as reflecting through a different point. And then you're doing composite. So composite, if you don't recall what a composite is, that's when you apply one mapping after another. So you'd apply the RO mapping first, and then you'd apply the TA mapping. And you just have to show that of doing RO and then TA is the same as RQ. Okay. All right. 16, let R be a positive number given an analytical definition of dilation by R with respect to a point Q. So in this one, you're taking what you've done before and you're actually writing out a formula for how you dilate from a point Q that is not the origin. It's basically a translation dilation, pretty easy stuff. And there you go. 16b as well. 17, let SRA be the circle of radius R and center A. Show that the reflection of the circle through the point Q is a circle. What is the center of this reflected circle? What is this radius? Draw a picture. That should be pretty easy to do. F be a mapping on its plane to itself. Recall the inverse mapping G of F is the mapping such that F of G is equal to G of F is equal to I. This is the identity mapping. The reverse mapping is denoted by F to the minus 1. This is all you need to know for exercises 18 through 21. So 18 through 21 you're going to think at a higher level here. This one should be complicated. The hard part about these problems is you need to use your symbols and think at a higher level. Don't get too stuck in the weeds. The previous problems will be the foundation for doing this problem. All right. And it's pretty important to see how you can translate a point and then reflect it to get the reflection through a point and things like that. Okay. 18 through 21, 22. There's a lot of problems here. This is a really long section. 22, let A equal A1, A2 be a point. Define its reflection through the x-axis to be the point A, minus A2. Draw A and its reflection through the x-axis in the following cases. That's pretty simple. 23, prove the reflection through the x-axis is an isometry. All you have to do is prove that the distance is preserved. Distance between 2 points, not the point and its mapping, but a point and another point and the distance between the reflection of that point and the reflection of the other point. 24, define reflection through the y-axis a similar way, prove that it is an isometry, same thing. 25, recall that a fixed point of mapping F is a point P such that F of P is equal to P. Using the coordinate definition, determine the fixed points of a translation, reflection through O, reflection through an arbitrary point P, reflection through the x-axis and the y-axis, prove your assertions. Yeah, 25 should be relatively straightforward. It might be hard to put the proof together, but it shouldn't be that hard. Probably 1 page max. 26a, let E1 equals 1, 0 and E2 equals 0, 1. Wow. This is the basic unit points of the plane. We call these the unit vectors when we do vector math. Plot these points. If A equals 1, A1 comma A2, prove that A is equal to A1, E1 to A2, E2. Yes, please do 26 and memorize these results from 26. Very important. When you get into vector math and you get into matrices, problem 26 is really important. And instead of like writing a section on, hey, let's do this, he's like, hey, I'll give you a problem. It's very easy and straightforward to figure out. 27, same thing. 28, same thing, building on the same thing. 29, we're using these E vectors all throughout though. Let the notation be as an exercise 29. What is the area of the dilated square? 31. Yeah, wow. Okay. Yeah, you're going to learn more in the exercises than you will in this section, just from the basic properties of addition, subtraction, distribution, stuff like that. So yeah, 28, 26 through 34, very, very important problems. Three-dimensional case, very interesting. I won't go through it. There is this section at the end of the three-dimensional case. Write all this up as if you were writing a book. Part of your mathematical training should consist of making you write mathematics in full English sentences. This forces you to think clearly and is an antidote to slapping down answers to routine plugging problems. As you will notice, carrying out the theory in 3 space amounts practically to copying the theory in 2 space. There is nothing wrong or harmful in copying mathematics. Do you know one of the means Bach used to learn how to compose? If you don't know, Bach is the greatest, probably the greatest composer of all time. He basically was the bookend on the Baroque period of music. So Bach, how did he learn to compose? He copied music. He memorized music. He played everything. He copied practically the entire works of Vivaldi. Some 300 years later, rock musicians still use approximately the same technique on each other. Yeah, if you want to get good at math, just see what the masters have done, copy them. Write this all up as if you were writing a book. If you can take it to the level of rigor that this book is, if you can make your stuff sound like math in English, if you can explain it to your friends and neighbors, you've really mastered the topics. If you can't, then I encourage you to slow down, study these things until you can. This is the difference between getting a 90% on a test and 100%. Okay, if you're so conversant in these theories and you're able to put things together so clearly and succinctly, you'll be able to breeze through the tests. So that's what I encourage you to do. I'm going to share a quick story from my history, and I might identify myself too much by this story. We were taking a test in physics, and I was at the time learning how to use LaTeX. LaTeX is a program to typeset mathematical equations. I encourage you to learn it if you want to actually typeset mathematics. Anyway, so we took the test. I finished 30 minutes early. It was an hour-long test. I think it was a midterm. It may have been. So I came back to the physics students' lounge, and I was bored. So from memory, I wrote down all the problems from the test in LaTeX and my solutions. And then when the students are coming out, I handed them printed copies of what I just did. I printed it out and gave them the solutions. I think I only got like the first 3 done. There's like 4 or 5 I couldn't. I ran out of time for the 4th and 5th. And I handed this out to them as they came into the student lounge after the test. And they said, "Where did you get this?" And I said, "I wrote this." And they looked at me with the most, they had a vision of disgust. They're like, it looked like an answer key. It looked like something I copied out of a book, you know. But there are, of course, mistakes that I would make as an undergrad. But if you can't do the math at that level, you don't really understand the math, is what I'm saying. And so it takes time for your brain to understand it. You have to copy. You have to repeat, you have to read, you have to think about these topics deeply. What is the famous, the quaternions were discovered by this Scottish mathematician and written on the bridge where he was walking. Because as he was walking, he was thinking about this problem he was trying to solve. Anyway, with that, I've wasted all of your time. Hopefully you guys enjoyed this episode. I know it's long, the exercises are long. Go through the exercises, take the time to enjoy and savor each one. And take care, guys. Bye-bye. Hey everybody, thanks for watching. This is part of a series on Sergey Lang's Basic Mathematics. You can catch the playlist over here, and you can find out how to support my channel over here. Thanks so much. Have a great day. Bye-bye.